All right, so it's always a pleasure. It's always the happiest day of an advisor's life when their student is presenting the work that they've been working on for many years. So let me first introduce Mike, and then Mike's going to take it over from there to present his dissertation work. And then after that, there'll be a time for Q&A. So please refrain from asking questions until the Q&A session. But by way of introduction, Mike came here to the University of Michigan in 2009, so he's been here almost half a decade. He completed his undergraduate work at Drexel University in Philadelphia, Pennsylvania. He received his bachelor's and his master's degree from Drexel in architectural engineering, so a little bit different than civil engineering, but very closely related. And that was one of the attributes that I really got excited about when Mike applied here. In fact, I first learned about Mike when an advisor that he was working with on research, Professor Ahmed Akhtan, actually called me up and said, hey, I have a great student, Mike Kane, who wants to come and work with you. And I was like, wow, why would this famous movie star want to come work with me? And then I realized it was a different Mike Kane. It's a Kane with a K, not a C. Anyway, so since Mike's been here, he's been working very hard in the area of control theory and system theory applied to civil engineering applications, and specifically undertook the design of some wireless sensing hardware that was designed from the ground up very explicitly for the applications that we presented today, which is essentially use and feedback control systems. Outside of school, Mike is a particularly well-rounded individual, so I got an opportunity to learn quite about him and his interests outside of the school setting. He's an outdoors guy, he likes to travel, been on a number of trips to Taiwan together. And he's also an entrepreneur and hacker, so he's really into embedded systems, so it's kind of cool to see that among students. So, at any rate, I don't want to steal his thunder, but it was a great pleasure working with Mike through these past 5 years. I've learned a lot and had a lot of fun doing the things that we've been playing with. So, after this, he'll go on to ARPA-E as a fellow. He's one of 2 fellows selected nationally this year to become fellows of ARPA-E. Very, very prestigious position. So without much further ado, let's welcome Mike to his dissertation.
Thank you, Professor Lynch. So yeah, I'll be presenting on my thesis work. Thank you all for coming. On wirelessly enabled cyber-physical systems, or wirelessly enabled infrastructure systems for civil engineering. So all this work has kind of been motivated by some grand challenges. And those grand challenges, there's many in civil engineering of restoring and improving our urban infrastructure. But the 3 that I'll kind of draw attention to are building energy usage. 41% of the entire energy used in the US is by building mechanical systems. So it's a really easy target to make a more efficient system or drop the US energy consumption. And a lot of the buildings in the US are relatively old and using old legacy controllers that are inefficient. With respect to kind of transportation systems, a lot of you are familiar with a lot of the bridges across the US are structurally deficient or functionally obsolete, so they're not meeting the demands that are being put on them. So we need methods that can identify degradation and detect overloads in these bridge structures. And then lastly, not traditionally in the realm of civil engineering, but it's a large-scale infrastructure system, and that's the electric grid. It has new kind of pressures being put on it by renewable energy, so they're unpredictable, especially with respect to wind. There's new loads that it wasn't originally designed for with plug-in electric vehicles, so that's putting new loads on the grid. And then there's the issue of grid security that that's been coming more and more into the news. So one way that we can tackle these problems is through enabling technology in kind of 3 different fronts. And all of these are kind of exhibiting some sort of Moore's law behavior. That's rapid or exponential improvement in metrics with respect to these technologies. So in wireless networking, it enables a flexible topology that we can communicate in a very flexible way. And the main improvements have been in creating low-power devices. And they can fit in small integrated circuits, so we can drive the communication as low down into the physical system as possible. With respect to embedded computing, main improvements have been in creating low-power real-time computing devices that, once again, they're fitting very small that we can fit entire systems on a single integrated circuit. And then lastly, there's 2 fronts in portable energy. There's energy harvesting with respect to solar and vibration, where we're seeing dramatic efficiency improvements. And then especially with respect to batteries in energy storage, we're seeing very impressive improvements in energy density by other researchers that are coming to commercial viability. So how do we apply these enabling technology trends to the grand challenges? Wireless networking enables us to kind of track people throughout a building and create personalized environments. So we're creating an efficient control system right around the person. And that requires advanced controls that really leverage the embedded computing. And then lastly, with portable energy, we can increase the sustainability and really put dense sensor distribution throughout the entire building. With respect to structural safety, wireless networking allows us to put sensors pretty much anywhere in a we can even track mobile loads. With respect to embedded computing, we can do in-network data processing, so only the processed data comes back to us and really reduces the amount of data that we have to process in our centralized systems. And improvements in energy harvesting, especially here at the University of Michigan, we've recently seen of vibration energy harvesters that enable wireless sensors out into the field for long periods of time. And then with respect to grid reliability, once again, we can track mobile loads with wireless networking. The embedded computing enables us to have a decentralized load control, so smart refrigerators and stuff like that, and use predictive control too, distributed throughout the electrical grid. And then with respect to portable energy, we see grid balancing with respect to batteries and increased sustainability with solar panels and renewables. So you see a bunch of physical systems that are highly interconnected multi-physics systems with kind of complex interconnected new technologies. So these all kind of fall under the realm of cyber-physical systems. And that's where we have a synergy between a physical system. So we have some complex physical system, or even systems of systems with multiple like hierarchical structure. And those are connected through some sort of boundary between the physical layer and the cyber layer. So we have sensors and actuators that are coming to this boundary point. And then traditionally, we would have some sort of tethered system that comes to separate controllers for system 1, 2, and 3. And these controllers then will allow feedback loops to improve the performance or get our objective in these physical systems. And then we can have a back end here with cloud computing user interfaces and just kind of back end or what would be front end stuff on the cyber side. But the future of cyber-physical systems, and what my research really hopes to do, is to drive the computing down as close to these nodes as possible. So here you see centralized memory and processing. And then we take that and we take each one of those memory and processing. We have the same amount of computational capability, but it's now distributed across the network and driven as close as possible to physical systems. And then, so that kind of leaves this whole area open here for what cyber modules do we embed into these computational components. So the first goal of my research was to develop a platform for these that enables these nodes to communicate amongst each other. The current market does not have such a platform, not even for researchers. The second is to develop the first cyber module here for controlling a certain class of nonlinear systems, and that's a bilinear system that I'll explain a little bit later. So this is just a localized controller. But then how do we distribute this controller for even more complex networked hybrid systems that we see a lot in infrastructure? Then all of this is going to be motivated and applied by a problem with the US Navy, where they have a new initiative of the integrated all-electric ship. So we have a very highly interconnected plant that's on board one of these Navy ships. But it's also analogous to a lot of the other problems that we see in civil engineering. So a quick overview of the presentation. First, I'll cover Wireless Cyber-Physical Systems platform that I led the development of, give a little bit of the motivation with the US Navy application, talk about kind of local bilinear controls, and then extend that to distributed control systems. So the first research goal is a wireless cyber-physical system platform. So we need something that can really drive the computing down as close to the physical system as possible and has adequate communication between each node. So why wireless communication? Is because it lowers costs because we don't have to we don't have to have the manual labor associated with installing wires, especially for large-scale systems. So it brings scalability. And then here we see a kind of a schematic of a centralized system that's abstracted into a distributed system where we have the same amount of computational power, but now we have resilience because we don't have a centralized point of failure. So the military is really interested in that aspect of it. And we have mobility too, so we can track both mobile and stationary systems. In the state-of-the-art of wireless cyber-physical systems, we have kind of three thrusts. The first one is wireless sensing, where the main research areas are on ease of use and power management. The second one is really leveraging the embedded computing and using that to process in network the data. So there's a research area on heterogeneous distributed low bandwidth algorithms. And then lastly, kind of using that processing power in a closed loop to create a feedback control system where the open research areas are in performance and scalability. There are some devices on the market. So here we see commercial off-the-shelf wireless sensing devices from a handful of companies. They're low power. They're really easy to use. They can be deployed by a civil engineer. Just go out simply in the field, put the sensors where you need them, and you can get the data that you need. But some of the drawbacks of them is they're closed platforms, so they have limited flexibility. They're pretty application specific. They're not massively scalable, and they have a fairly high latency from the time that the sensor data is actually taken in the field to the time it's returned to your centralized processing repository. And because of that latency, they really don't have the option for feedback or feedback control. To kind of overcome some of these challenges, researchers have developed a handful of platforms also that have been used in civil engineering. The iMote2 is a fairly computationally powerful device. I think it's running at a couple hundred megahertz. And at UIUC, they've developed a structural health monitoring board to apply this to measure responses of bridges. But one of the drawbacks of this is it uses kind of an obscure operating system that's not real time, so it's difficult to do control of fast systems, and it uses a non-standard programming language in that operating system. Other researchers have developed, like here at the University of Michigan, we use the Narada a lot, which is an 8-bit microcontroller, which has minimal computing power. We've seen some interesting things out of Los Alamos National Lab, sensing ultrasonics, so we can it's introduced some new areas. And then there's even some commercial open devices for developing your own kind of wireless sensing platform. But once again, they have relatively low computing power. There is an area of commercial wireless control devices. It's standardized as ISA 100. It's commercialized as wireless HART. HART is an industrial control standard for wired control system, and they extended it so you could kind of have a heterogeneous network of your wired industrial control system with some wireless sensors. It's very robust, uses mesh communication, except there's a significant latency that makes feedback control relatively difficult of quick processes besides slow thermal chemical processes. And it's really difficult to leverage the embedded computing within these nodes. The manufacturers actually recommend that you don't develop custom hardware for these devices. So we can kind of combine all of those cons that we saw earlier into kind of needs that the wireless cyber-physical systems community needs. And the reason we need these is because we're limited without them. We're unable to control nonlinear plants in an autonomous manner, especially for large-scale civil infrastructure. We need something that can respond quickly to mitigate the effects of cascading failure and be able to stabilize systems that could potentially have thermal runaways. And then also we need something that can be implemented by civil engineers with a relatively low learning curve in order to reduce implementation costs. Civil engineering is a very cost-oriented area. And then lastly, we need something that's flexible, can be applied to many different application areas, and something that can be easily programmed even out in the field. So how do you design a new wireless node for cyber-physical systems? Well, there's two main things that you need to consider. One is what sort of wireless protocol you use, and the other one is what sort of computing you use. So you're probably pretty familiar with 3G and LTE on your cell phone. You probably have Wi-Fi in your laptop that works pretty good throughout your house. And you probably have Bluetooth on your microphone in your car. But there might be something that you're not aware of called Zigbee. So it's similar to Bluetooth. It uses the same radio frequencies, except it's ultra low power, so we lose a little bit of bandwidth. And you see that the range scale is only about the size of a room, maybe a building. We have gotten kilometer scale distances, but that's pretty for like big open air between bridge towers. But we can use a mesh networking protocol where we communicate from one node to the next, because the nodes will always be kind of within the scale of a room together. And we can communicate over a large-scale system just by neighbor-to-neighbor communication. So this Zigbee is what I decided to embed it into this new wireless device. With respect to computing, the Narada and many of the other wireless sensors on the market use 8-bit microcontrollers. The iMote used a 32-bit microcontroller, almost like a single-board computer, but more of a cell phone chip, so there's kind of an area between. And obviously, we're not going to embed multi-core servers into each one of these different nodes. So we need some sort of balance between all of these things that improve as you go out this way, or increase as you go out this way. I found a nice balance in this 16-bit microcontroller from Texas Instruments that can handle floating point calculations and has relatively good power numbers so that we can have battery-powered operation under certain circumstances. So this all kind of came together into the Martlet wireless device, which is what I've led the development of. So it's able to meet the needs of the wireless cyber-physical systems community. It has a dual-core 16-bit microcontroller. The first core has a typical pipeline processor with a floating point unit. The second core is a floating point control law accelerator, so it's just meant for local control loops. So we can have local control loops in the secondary core, and we can have distributed algorithms running in the primary core. I've reduced the latency through designing a very light RF stack. It doesn't have an operating system. It just runs on a state machine, so we have very little overhead on the software side, so we can service interrupts relatively quickly. And the programming language is C99 compliant, which civil engineers are becoming more and more familiar with. The hardware architecture is extensible. We can plug in these custom boards into these 4 connectors at the top. It has a 16 gigabyte SD card, so we can store a lot of data on the node before it's relayed back. And then it's easily programmable. All you have to do is plug this board into the bottom and plug your micro USB connector into your laptop, and it's just like developing C code on your laptop. So like I said, it's a very extensible platform. And over the last 2 years since it was originally developed, we've created a lot of what we're calling Martlet Wings, or these extension boards that we can plug on top. So we have battery boards that we can plug underneath that can do battery charging, prototyping boards that have a nice little breadboard, and then some application-specific ones where we can measure, or we have smart anti-aliasing filters that can change the gain and bandwidth. We can measure acceleration, temperature. We can control pumps, valves, motors. We can do environment monitoring. And at Georgia Tech, we have collaborators there that are working on ultrasonic capabilities on this board. But with all of these boards, we need some application area to be able to test them. And the very first place that the Martlet was tested in a field-like condition was at Los Alamos National Labs in the harsh conditions of the New Mexico desert on this 12-meter tall wind turbine tower. We wanted to kind of monitor the performance of this tower. So we embedded, because of the harsh conditions, we put a Martlet, an anti-aliasing filter, and a triaxial accelerometer inside of one of these weatherproof boxes and mounted 6 of them on this wind turbine. The goals of this testing were mainly as a field validation of the Martlet, but more specifically, 2-axis acceleration at a fairly high sampling rate for a wireless device and for a multi-day testing. The reason we're sampling is so high is because the turbine can spin at up to 500 RPM, which is pretty fast for something that big to be spinning around. The experimental program is to collect 12 seconds worth of data every 5 minutes over a 3-day period. And then we can also manually control the server in order to get data at interesting environmental events, such as when we ramp the speed up or when we apply a brake to the turbine to ramp it back down. So here we see some time histories of the data, where you see at the base relatively low vibration, relatively high vibration on this side. So the wind is blowing in the X direction, but you see vibration back and forth in the Z direction at the top of the tower due to the imbalance in the rotating machinery at the top of the wind turbine tower. If we look at this in the frequency domain, we see this is in the time history, and this is a periodogram or a spectrogram of the data. So this is frequency versus time. You see that the frequencies change, and there's very high frequency characteristics. There's a 250 hertz anti-aliasing filter, so you don't see anything above this. The data was collected at 1,000 hertz. But if you listen to the structure while it's running, you can audibly hear the structure vibrating. But what we see is as the frequency changes, the amplitude changes, which tells us that there's some sort of resonance happening between the vibrating machinery at the top and the response of the entire structure. If we do a modal analysis, we see 2 different modes at 1.5 and 2 hertz about that are pretty orthogonal and pretty much what we would expect out of this structure. Then we see a third mode at 4 hertz, and it's slightly askew and pretty much a combination of these 2. And this is an operational mode shape. And where this comes from is the wind is normally blowing from the north-northeast. So we're mainly exciting the east-west direction due to the rotating machinery, but because the wind is a little bit askew of the structure, we're actually exciting this a little. So we actually see another mode due to the vibration of the system due to the rotating machinery at the top. With respect to long-term trends, so this is a long-term periodogram where we took from 0 to 10 hertz, starting September 16th, going all the way to September 18th, and comparing that to weather data. So we see the 1.5 and the 2 hertz peaks in our frequency, but we see here changes in this frequency here, which are highly correlated to the wind. So that, once again, tells us that this is an operational mode shape that is correlated to the wind speed, which is also correlated to the blade speed. We really would have liked to measure blade speed, but it just wasn't possible. So this is just one application area of many that the Martlet could be applied to. In the second area where it was applied with the help of Machiros for a collaborative project here, an experiment was designed to study the diffusion of CO2 gas in an enclosed room. So if you have a single person breathing in the middle of an enclosed room, how does that CO2 gas kind of diffuse? And then that model was going to be used for later HVAC system design. So instead of just having a person sit in a room for hours on end, completely sealed off, we created a an analog of human breath, where we have a tank of 5% CO2 gas in air and bubble it through water that's at 100 degrees F, and then comes out as a 100% humidity gas that has a constant CO2 concentration of human breath. So this is being pumped into this closed-off room, and then we have 2 columns that have CO2 sensors on them. We have 12 CO2 sensors in 2 different columns, and there's 3 Martlets. So we're actually multiplexing these CO2 sensors on each individual Martlet using this interface board designed here. So here are the experimental data compared against the computational fluid dynamics model. So this is the bottommost node that you see here, a time history of it. You see very high concentrations for this near column, and then on the far column you see very low concentrations close to that. As you proceed a half hour later, you see that at the very top you see it increasing a little bit more. So once again, this is just another application area that the Martlet can be applied to. So to kind of summarize the developments of the Martlet, so I led the creation of this device in collaboration with a couple other universities and created a device that really meets the needs of the wireless cyber-physical systems community. I validated its reliability and platform extensibility on 2 different test beds, but none of these test beds have really fully utilized the feedback control capabilities, the ad hoc communication, or the dual core processing, which are all really kind of core focuses of this thesis. So we need some sort of application to motivate really a challenging problem to apply this wireless device. And I found that in this US Navy initiative for the all-electric integrated ship. So what this is, it's once again a system of systems, but more specifically we see an electric power system, we see a pipe network system pumping water throughout the ship, and then we see multiple thermal loads that need to be cooled. These thermal loads can be computers, can be HVAC systems, could be laser weapon systems. So here we see a water network and a heater network, and that's called a hydronic system, where we're using water to transfer thermal energy. So what is a hydronic system? Well, we see it in a lot of different other application areas besides the Navy. We see it in building systems and radiant floor. We see it in commercial or in industrial processes, such as power plants, where they act as a safety critical feature of cooling loads. So here they're meant for cooling, here they're meant for heating. But going back to the Navy application, it all stems from the integration of the traditional sense, where you have a propulsion system and you have an electrical system, and those 2 are isolated. And that was originally designed to be redundant, so one could fail without causing the other to fail. But with the kind of budget crunches that we're facing lately, the Navy is interested in reducing costs through automation and kind of combining systems together. So here you see a redundant electrical system and a redundant propulsion system, and then the ship service loads. But now this is all highly interconnected, and we need some sort of controller that can handle this interconnection and prevent cascading failures. And that's where this cyber-physical systems paradigm really is a good approach. So we have multiple plants. We install some sort of software framework on top of this, and then we have sensors and actuators. And what my research really hopes to do is to, first of all, introduce wireless telemetry, so we can really have wireless sensors and actuators throughout the entire system, utilize the embedded computing on each one of those devices, and then tie them all together in some sort of like computational cloud that's interconnecting the computational side with the physical side, creating a cyber-physical system. So this is a really good motivating example. And for that reason, I've created kind of a test bed of a hydronic system that's typically found on a Navy ship. And that's down in our lab. So it has 2 different pumps, which are analogous to the port and starboard redundant pumps that you would have on a ship. You see 4 different valves, which create 6 different pipes. You see 4 different thermal loads. So these thermal loads are paired together with a weak thermal interaction. They're just kind of epoxied together. And then underneath each one, we have a resistive heater. So the goal of this is to figure out how do we control these pumps and valves in order to efficiently cool these blocks, keep them below critical temperatures. This is a picture of the test bed. You see the 2 pumps, the 4 valves, the thermal loads, and you see these temperature sensors, some flow meters, which are all then going to a wireless sensor. So to kind of summarize this platform and this motivating, we found a good motivating cyber physical system example in the initiative for the integrated ship. I've created a test bed for wireless cyber physical systems that naturally decomposes and has all of the required aspects that we need. So what's ahead, both in research and in this presentation? A local bilinear controller was first developed and then kind of combined with hybrid systems and distributed control theory to create a wireless agent-based control system. And then that was tested experimentally. So the first part of that is, the first goal there is to create a bilinear control system. So bilinearity is a type of nonlinearity that shows up very common in many different civil engineering application areas. So looking at the Navy application, or the hydronic system, we have water coming out of this thermal block. We have temperature sensors on top, and we have a heater underneath. If we track the energy coming in and out of this block, we see that if the block is hot and the water is cold, the thermal energy will be removed through each one of these flows. Thermal energy will be coming in through the resistive heater, will be coming out to air, and will be transferring in between these 2 blocks. And we can model the block temperature with this differential equation where we just have the rate change in temperature is just the sum of these thermal energies coming in and out of the system. So if we combine all of this together into a state space model, we end up with this pretty nasty equation here, where we have our rate change of our state over here. We have our state vector over here. So this is a state space model if you're familiar with dynamic systems. And then we have our disturbance vector here. But what you don't see is our control vector. What we're doing is we're trying to control flow rate, but you really don't see that because what flow rate is analogous to are these heat transfer coefficients. So what we're actually controlling are the parameters within our state space matrices. And this is called a bilinear dynamical system, or a dynamical control system. It was initially introduced in the 1970s, but has seen more and more use with a nice comprehensive work by Elliott in 2009. It's a special class of nonlinear systems that can be decomposed into this sort of differential equation, where you have the state being multiplied by your control. And we see this in chemical, mechanical, electrical engineering applications, along with other biological processes. But because this system is so complicated, and I really want to just study kind of how bilinear systems can be controlled with embedded processing, I created a simple system that just has 1 pump, 1 thermal load with a heater underneath. So we just have this dynamical equation down here, where this is our control variable, the heat transfer coefficient, which is multiplied by our state. This heat transfer coefficient can be algebraically related to our flow rate, which can be algebraically related to our duty cycle, which is then just setting the pump speed. So we have, how do we model this system in a way that's useful for control and analysis? Well, there's 2 different approaches. There's the linear state equation, where we have x dot equals ax plus bu with some sort of disturbance. So this is pretty familiar. This is probably what you're pretty familiar with if you're familiar with state-space control systems. Our state, we're trying to drive to 0. We're trying to drive the block temperature to the set point. And our constraint is shown here, which is a pretty nasty constraint on our control. We have a maximum flow rate that we can produce, which means we have a maximum heat transfer coefficient. But our control is actually our rate change in temperature in this case. So our control always has to stay within this bow tie shape with respect to our state. So we have a pretty nasty constraint that's state dependent. And that can increase the computational complexity of solving an optimal controller. The other approach that we can take is we make a more complex differential equation here by multiplying our state by our control. But we end up with a really nice rectangular constraint that's time invariant, which I kind of had an intuition that this would make the optimization problem more easy, according to some of the assumptions of the iterative optimization process used to develop a controller. But how do you develop a controller? Well, there's multiple approaches you could take. I decided on a model predictive controller because it directly handles the constraints of the control system, and it can adaptively change to changes in estimated disturbances, to changes in models. So what is model predictive control? Well, what it's trying to do is it's trying to develop an open loop control sequence, or a schedule of what the controller will do from this point forward. So in 2 minutes, we'll turn the pump on, and then 2 minutes, we'll turn the pump off. So here we see a little schematic. We have our reference trajectory. We have our measured output in our control. If we just estimate that into the future, our predicted control is just constant from what we currently had, we can predict or create an estimate of this is what would happen. This would be our predicted output of our system. According to some cost function, we would have a cost of 1,000. We can optimize this controller to try to drive it a little bit closer to our reference trajectory, so we have a little bit more. So we've optimized our control trajectory to drive our cost down. And we can do that again to drive our cost down even more. And once we drive this down to as low as possible, we kind of wait for this time period to elapse. We apply that very first step, and then we redo this whole process. So this whole process is just happening at fixed time constants, or at fixed periods in time. But what is that control objective that we're trying to do? What are we mathematically trying to reduce? So I've looked at 3 different areas, and this is part of a parametric study between the multiple modeling approaches and the multiple objective functions that I undertook as part of this thesis work. The first objective is a minimum time objective, where whenever the temperature is above the set point, we want to drive it to that set point as quickly as possible. The second objective is a quadratic objective, which you see a lot in control literature, where you have your state, quadratic cost on your state and a quadratic cost on your control, which leads to a convex objective function for certain assumptions on Q and R, but the resulting optimization problem won't necessarily be convex. And then we have a very explicit efficient cooling objective. So this is exactly what we want. We only put a cost on temperature when we're above our set point, while here we put a cost on our temperature when we're above or below our set point. So we only put a cost when we're above, and we will put a direct cost on the power consumed by the pump. So I've analyzed all 3 of these throughout my dissertation, but I'll focus on just this middle one here for the purpose of a quick derivation. So first we'll look at that quadratic cost with a linear system model. So you have this dynamic model. You have this constraint, which is visualized here. You have some sort of objective function, which is can be in the form of a convex kind of surface like this. But then you have this constraint according to that dynamics here and according to this constraint on control, which can lead to a non-convex constraint where we might end up at maybe some sort of local minima instead of at the global minima that we would actually want. So when we analyze this controller later on, we really have to analyze it against benchmarks and see if we're getting the performance that we want and make sure that we're not getting stuck in a local minima during the optimization process. So we've taken this objective, it can be augmented. So we take the dynamics here and augment them with a second set of dynamics. And that second set of dynamics allows us to make the minimization problem easier. So this is the co-state, this is the co-state down here, and then we have the state dynamics here. And this minimization problem is now with respect to H as opposed to J. J has this integral here, while H is independent of that integral. So if we change U at one period, we don't have to worry about changing the effect of our control at another period. So it makes that optimization a lot easier. And this leads to the 2-point boundary value problem, where the solution of this meets the necessary conditions for optimal control. So the 2-point boundary value problem is we have our forward state dynamics. So we have some sort of initial state, the temperature that we're at now. We have our reverse co-state dynamics with some sort of final co-state, which is 0 in this case. And we want to forward integrate this, and we want to reverse integrate this, except you see that there's coupling in between these, and especially coupling between the feedback law. So we need some way to be able to, we don't know what P is here, so we can't forward integrate this. So we have to do some sort of iterative estimated process. So this is for the linear system model of the quadratic objective function. If we look at the bilinear model, we have the bilinear state equation. We have the very nice rectangular constraint on our control. We have the same objective function, except now U has a different physical meaning. Before, the physical meaning in the linear system was the rate change of, or the rate of heat being removed from the system, while here U is the heat transfer coefficient, which is much more analogous to our flow, and we're putting the penalty on much more of what we actually want. We end up with a very similar 2-point boundary value problem, except we now have a nice feedback law that has constant constraints as opposed to the time-varying constraints. So solving these two different two-point boundary value problems, we start out with assuming that the control is 0 over the predicted horizon. And then we forward integrate our state. So if we start at 10 degrees above our set point, and we forward integrate that, if we have like a heat coming into the system which is causing our temperature to rise. So we have an estimate of our control, we have an estimate of our state, so now we can reverse integrate our co-state, and then we can apply the feedback law, multiplying it by some speeds, let's say 10%, to try to reach more closely to our optimal control. And then we can iteratively do this process until we eventually converge to some control that meets the necessary conditions for optimality. So this is for the linear case, and then we see for the bilinear case a very nice convergence as opposed to banging around because of the changing constraints. So this two-point boundary value problem has been analyzed and created for both the quadratic case and the efficient cooling case. The minimum time case is actually much more simple. It just results in a bang-bang controller. So whenever you're above your set point, you just bang your control onto the maximum flow possible, and then that will cool your system to the set point as quickly as possible. With the quadratic case, we end up with different solutions for the linear and bilinear formulations because the weighting on the control is different. With the efficient cooling, we end up with a two-point boundary value problem. But instead of an algebraic feedback law, we have to solve a convex program at each step during the optimization. And then but we have the same solution for our linear and bilinear derivations. So if we look at some simulated results, this is the trajectory for 0 flow of a system that starts at 40 degrees, 10 degrees above the set point, and has heat being injected into it. This is the maximum flow controller, where the temperature eventually reaches some asymptote just below 30 degrees. This is the minimum time controller, where you get that bang-bang effect. So it's on at a maximum and then reaches some steady state once it reaches the set point. The quadratic linear controller controls the system, but it doesn't quite get us to the set point because it's putting a penalty on not exactly what we want. It's putting a penalty on the rate of heat being removed, and we actually want to put the penalty on pump power. The quadratic bilinear case gets a little bit closer to what we want by putting the penalty on the right thing, and we see kind of a little bit more of what we would expect out of this system. The linear efficient cooling is putting an explicit penalty on exactly what we want whenever we're above the set point in the pump power. And then the bilinear case lands right on top of it, showing that the two solutions converge, or the two models converge to the same solution. So to summarize, minimum time ends up in a bang-bang controller. Quadratic ends up with two different solutions that have different computational complexities, but they're relatively close, where I'm measuring computational complexity in just CPU time on a PC. And this computational complexity is important because it's what is really the constraining factor on implementing this on a low-power wireless node. And then what I've selected as to go forward with is a bilinear efficient cooling. It kind of balances the computational complexity. We get explicitly the objective function that we want. And the solutions, I can reliably see that the two solutions converge to the same. So running an experiment, this was all embedded into a single Martlet. So all of that optimization was embedded into the 16-bit microcontroller and run in real time in a model predictive framework. So here you see the black measurements of the temperature and the flow rate that was actually produced by the system. You see the MPC trajectory from the very first step, where the MPC trajectory predicts that the temperature is going to go down here, and it predicts that there's zero control. So the green background means that the heaters turn on. So the controller, when it starts here, doesn't realize the heater is going to turn on here. It just assumes it's going to keep on going. But if you apply these MPC periods and move forward in time, you will it'll keep on predicting wrong until it gets to this point right here, when it realizes that the heater's turned on, and get a new estimate of what it should actually be doing, and then it actually turns the flow on in order to keep the temperature below the set point. That keeps on happening until the heater turns off, and we get this new update to realize that the system has changed. We're not quite getting the flow that we want, but this is actually one of the good features of model predictive control, because this is an experimental issue where the model doesn't quite match the physical system, but you can see that we're still receiving the performance that we want because we're constantly updating this open loop control. And then you can keep on going through, and you see that the performance, and you see all these open loop MPC trajectories that change every time the system changes because the heater turns on and off. So summarizing these bilinear model predictive control developments that I've made, I've analyzed multiple approaches to analyzing bilinear or controlling bilinear systems, both with linear and bilinear models and multiple objective functions, which is kind of bringing that are all kind of balanced against the constraints of embedded control systems. I've embedded this model predictive controller into a Martlet and tested it experimentally. And one of the really neat developments here that I haven't seen before is implementing a GNU scientific library into a 16-bit microcontroller to control these infrastructure systems. And then what I didn't talk about is that it's actually implementing a fast MPC, or a fast model predictive controller, where that 2-point boundary value problem isn't converging all the way. It only converges until time runs out, and then it updates the system. And it's actually still able to control the system without fully converging. So what I just kind of discussed was a very simple controller, one pump, one valve, one block, like this. But I've ignored everything else. So how do I extend this in order to control this entire complex system? And that's where distributed controls come in. Centralized systems aren't scalable to the size of civil infrastructure. So hybrid systems are also a characteristic nonlinearity of these large-scale systems. So what are hybrid systems? They're a dynamic system that has continuous inputs and discrete inputs, continuous outputs and discrete outputs, and some sort of dynamical system in between. Because we have the discrete characteristics, we kind of lose some of the what we would normally expect out of a continuous system. In a continuous system, you would not expect to see state jumps like this in your continuous state. And you also wouldn't expect to see kinks in your continuous state. And these violate the Lipschitz conditions, which are commonly used for analyzing continuous systems. So we kind of lose some of the tools that we have normally for analyzing and developing controllers. Some additional challenges is we can exhibit Zeno behavior in hybrid systems. So if this ball were to switch the kind of model that it uses every time that it bounces, so that every time it hits the floor, it has to switch a model to bounce back up, you actually have infinite switching in a finite period of time, which you can imagine is very difficult to numerically simulate. And then you can also have non-determinism, where if you have two switching surfaces intersect, when the trajectory reaches that intersection, you don't necessarily know which way, or it's highly sensitive depending on which way it goes. So how do you model these systems? If you have a very simple framework that meets the framework of piecewise affine, there's a good mathematical relationships for that for analyzing these systems. There's mixed logical dynamical systems, which have there's plenty of software packages available for analyzing those. But those software packages are meant for multi-core computers, which really aren't applicable to embedded systems. And then there's hybrid autonoma, which what I've decided is the modeling approach to use. So what is a hybrid autonoma? Well, it extends the state machine concept that's commonly used in computer science. So here we see 3 different discrete states in our state machine. But then besides the discrete states, we also have continuous states in Rn. Within each one of these discrete states, we have flow conditions for our continuous state. So we have our differential equation, we have an initial condition, and we have some sort of invariant that will always stay within each one of these discrete states. We have guards that specify whenever the continuous system matches one of these guards, it'll force a discrete state transition. So when the discrete state reaches this guard, it'll transition from this state to this state, or this state to this state. During that transition, you can have a reset, which resets the continuous state from so you'll see a jump in your continuous state. Analyzing these controllers in general is an NP-hard problem, which means that it's highly computationally complex. We can use tools such as mixed integer nonlinear programs. So once again, those require computational capabilities that aren't available on an embedded node. We can leverage special forms of the physical system, such as like timed autonoma, which make analysis more robust. Or we can use abstraction and simplification, which is one of the approaches that I've taken. And one of the approaches of abstraction is through agent-based abstraction, or agent-based distributed control. So here we see a centralized control system, a decentralized control system where there's no communication, and then we have a distributed control system where it's very similar to decentralized, but now we're exchanging information to improve performance. So why distributed? Well, we have resiliency because we don't have a centralized point of failure. We can increase response speed because we've embedded that computing as low down into the physical system as possible. And we have increased scalability because we can distribute the system over large physical scales. If we embed an agent into each one of these nodes, and an agent is something that acts autonomously to maximize its utility. And that's where agent-based control comes in. And these utility functions for each one of these agents is designed by the control engineer so that when all these agents act together, they reach some sort of global control objective. And they communicate with other agents in order to gain information to improve this, their personal utility. So I've taken this agent-based framework and applied it to the hydronic system from the Navy application. So here you see that test bed down in the lab again, where we have a single agent controlling both pumps. We have a single agent controlling the 4 valves. And then we have 4 agents for each one of the thermal blocks, which are measuring the temperature and generating some sort of desired flow rate. The first agent that we'll look at are the thermal agents, which can be modeled as a timed automata, where they just pretty much iteratively do this process. They do the MPC process at a fixed period of time. So this is pretty much just doing the entire MPC section that was previously presented. But it's agnostic to the supply side. So here you see a complex like supply side where you have 2 pumps and valves. Assuming a certain valve configuration, this block doesn't care how these 6 pipes get the water into this block, but it has some sort of estimate of what sort of power would be required for that. So what it does is it generates a desired flow that it wants through its block. Then the kind of balancing agent to that on the supply side, so the thermal agents are kind of a demand side. This is the supply side, where we have, once again, a timed automata modeling where the agent is just requesting these desired flows from each one of the 4 blocks. Then it's solving a convex program of minimizing the pump power so that it meets the desired flow. So even if it can't necessarily get exactly the desired flow, it'll always get at least the desired flow in each one of the blocks. So this flow rate is then algebraically related to duty cycle and then to pump speed. And then we have, lastly, the valve agents, which really bring in the hybrid dynamics. So everything that we saw previously was continuous control of the transients, assuming a discrete state. Then the discrete control of the valves is controlling for steady state efficiency. And this can all actually be pre-computed ahead of time, really lessening the load on the valve agents. So they have computational capabilities for other in-network data processing. So this is the pre-computed feedback controller control graph for steady state optimality. Then whenever they ask the heaters, because the heaters are relatively constant, but they switch on and off, as we saw previously. So whenever they ask the heaters for their updated state, they look up in this lookup table. So let's say the first heater is on at 15 watts and the second heater is on at 1 watt. So we see this blue area up here. We match this to this blue area here, and the first 2 valves should be turned on. So mainly when this heater is only turned on, we see just the one side of the system activated. But if the other side of the system is hot at all, then we see all 4 valves open up and the entire system being cooled throughout the entire network. So this agent-based control architecture was distributed in a series of martlets and applied to that Hydronics test bed down in the lab. And here we see the experimental results. So this is a graph of the block temperature for each one of the 4 blocks. The black line is the measured value. The colored lines are the MPC trajectories. They turn red as they move forward in time. And we're reaching pretty close to our 40-degree set point, mainly below it. Here we see the block flows for each one of the 4 blocks. And the gray line are what the blocks request. The black line is what is actually delivered to the blocks. And because the supply side has constraints, there's only 2 pumps, and we want to be able to get 4 flows exactly as what the blocks desired. We won't meet that, so we always just make sure we meet the desired flows. So the gray line is the desired flow. The black line is what was actually produced. And this is where some inefficiencies in this control architecture come up. So the agents assume that so much energy in the entire system is being consumed as the integral underneath this area pretty much. But the actual energy consumed is the integral underneath the black area. So we've lost some of the efficiency in the agent-based abstraction because the agents weren't aware necessarily of what all the other agents were doing. So we have to really compare this because we know that we're not quite optimal, but we still have to compare this against other benchmark controllers to see how we perform. So I've done that in simulation by comparing. So this is experimental results, but the parametric study, the benchmark study was done in simulation. So I've compared it against bang-bang controllers and 2 other centralized and agent-based model predictive controllers that have a constant prediction history. So the MPC assumes that the control is constant over the open loop trajectory. So all of these colored lines would be horizontal. They wouldn't curve at all. So there's some optimality in that constant assumption. So we see and because each one of these has a different objective function, it's really not fair to compare what these controllers are doing to each other because they're trying to do different things that are all slightly different. So what we do is we compare all the apples and all the oranges and all the fruit kind of together to each other. So here we see the minimum time objective. So this is the amount of time spent above the set point. The minimum time controller does a pretty good job at that. And the proposed controller kind of falls in the middle of the pack. The previously published objective function, the proposed controller actually outperforms the other controllers on what they're trying to do, and which is a pretty good result from the proposed controller, but it shows the suboptimality in the other controllers. And then here we see the bilinear efficient control, which is the objective function that the proposed controller is using, and it outperforms all of the other controllers pretty significantly on that objective function. And then with respect to computational complexity or CPU runtime, the proposed controller kind of falls in the middle of the pack and is much better than the other agent-based solution. So to kind of summarize this agent-based control architecture, it controls both hybrid and bilinear dynamics in a global complex control system. I've embedded this agent-based controller into a network of martlets to distribute the model predictive control problem. And it has both timed and event-based wireless communications. And then this was experimentally tested on the Hydronic Systems test bed over a 45-minute long experiment of the block temperatures being turned or going up and down, showing that it performed well compared to all of the other benchmark controllers. So to summarize, this is kind of the framework that I've been building on throughout this presentation. And the very first thing that I developed is I led the development of the Martlet wireless sensor, which kind of really introduces new realms for cyber-physical systems, because we have larger computational capabilities right at the nodes, and we still have communication between us. So we can really distribute the computing and increase resilience and response speed of local control loops. But the second development was mainly in the parametric study of bilinear control systems, comparing them against different metrics that are important for distributing across these types of embedded controllers. And then this local control was distributed across a large-scale system that also exhibits hybrid nonlinear dynamics. So this kind of shows all of the developments that I've made throughout my thesis work, but there's still definitely open areas. And one of those open areas is model updating. And I've done a little bit of work on this, but haven't shown it. And this is important because each one of these control architectures are model-based. So if we can improve the model by seeing how the system performs and improve the model, we can update these models that these other controllers are using and improve the entire overall system performance. And then another opportunity for future work is on kind of more of the intranet or the computation that's further away to really leverage all of the computing that's available throughout an extensive network and bringing human into the loop, or what's sometimes called cyber-physical social systems. And then also accounting for cyber-physical security, so different ways that these systems can be compromised. And then lastly, the future work of the entire pretty much CPS system community is to create a unified science of all of this, to cope with the complexities and the difficulty of predicting the behavior of these complex systems, and to generalize application-specific development. So I've tried to do that with the bilinear system developments. Bilinear systems show up in many different application areas along with hybrid dynamics. So we're moving forward in this area, but there's still definitely a lot of work to be done. And to kind of come back to what this work is really meaning to do, it's to solve these global grand challenges of improving our urban infrastructure by applying these technologies in a smart way. So I'd like to thank you all for coming. I really appreciate having a full room here. Thank my support from, or the financial support from NSF, NIST, ONR, and then also from a couple of university grants. My advisor, Professor Lynch, has been great throughout this process. I've learned a lot from him, both on the technical side and also on just everything else about engineering and dealing with all the complexities of life. My committee members, Professor Younghans, Professor Lee, Professor Scruggs. Scruggs has been especially helpful in the development of the analytical analysis of the control problems. The entire LIST lab cast of characters. My parents, family, friends for understanding what I'm doing at 3 a.m. when I'm not home yet or calling home. So, then my collaborators at Georgia Tech and Michigan Tech have been working on the Martlet with us. I've kind of led that 3-university team. Robert Gordeckers, who are here, who has really helped on the initial development of the Martlet and helped with all those little bugs on a circuit board. Professor Thune, who couldn't make it today, as professor in architecture, has really introduced new, interesting control problems to me. Then I've collaborated with some work outside of this thesis with Professor Law and Professor Lowe at Stanford and NTU. At the Naval Surface Warfare Center in Philadelphia, they're the ones that really brought us the Navy application system, and I've been to their facility a couple times to test these. And then Andy Zimmerman at Civionics, who's really been supporting the Nerada side and kind of helped me on the embedded development side also. So thank you all for coming. And